Have you ever looked at the sun and wondered what secrets lie beneath its blazing surface? It's more than just a ball of fire in the sky. It's a massive nuclear engine, a boiling storm of plasma, magnetic fields, and mysterious phenomena we're only just beginning to understand. Today, we'll dive deep into the heart of the sun, peeling away its layers one by one. This isn't just a journey through space. It's a journey through time, through energy, and through the invisible light that reveals the sun's most hidden features. I'm Alex McColgan, and this is Astrum. Let's explore our star, not just in visible light, but through the full spectrum of electromagnetic radiation. You're about to see the sun like never before. When we gaze up at the sky, it's easy to take the sun for granted. It rises, it sets, and we move on with our days. But in reality, this unassuming yellow disk is a titanic powerhouse, the very engine of life on Earth. It is a ball of plasma so massive that it contains 99.86% of all the mass in the solar system. It's responsible for Earth's climate seasons, weather patterns, photosynthesis, and the very possibility of life as we know it. Yet for much of human history, the sun was a mystery, worshipped as a god, feared as an omen, or simply admired as a glowing, untouchable presence in the heavens. Now, thanks to advanced science and space telescopes, we can finally begin to understand this colossal sphere in a new way, not just by looking at its visible light, but by observing it through the entire electromagnetic spectrum. In this video, we will explore the sun, not just as a bright object in the sky, but as a living, dynamic structure with layers of energy, motion, and magnetic chaos. The sun, categorized as a G-type main sequence star or yellow dwarf, might seem average on the cosmic scale, yet to us, it is everything. It burns at a core temperature of over 15 million degrees Celsius, fusing hydrogen into helium in a relentless nuclear reaction that has been burning for 4.6 billion years. And despite being so unimaginably hot and active, the light we see from it is already old, around 8 minutes and 20 seconds old to be exact. That's how long it takes light to travel the 150 million kilometers between the sun and Earth. But here's a mind-blowing fact. The photons that finally escape the sun's surface and reach us today may have been created over 10,000 to 170,000 years ago in the sun's core. They've spent eons bouncing from atom to atom, weaving their way through layers of plasma before finally breaking free. And now, thanks to instruments like NASA's Solar Dynamics Observatory, we can trace their path backwards, peeling the sun like a cosmic onion from its outermost atmosphere to the boiling photosphere, and we'll do so using the full power of light itself. We humans perceive only a sliver of reality. The visible light our eyes can detect, the warm yellows, the cool blues, the fiery reds, is just one small slice of the vast electromagnetic spectrum. Beyond this narrow band lie powerful wavelengths like ultraviolet X-rays and infrared, each carrying its own secrets, each revealing a different face of the universe. When it comes to studying the sun, these invisible forms of light become our most powerful tools. NASA's Solar Dynamics Observatory, or SDO, has been capturing images of the sun across multiple wavelengths since its launch in 2010. It's as if the sun is speaking to us in many languages at once, and we've finally begun to understand what it's saying. By observing light at 19.3 nanometers deep in the extreme ultraviolet range, we uncover the sun's corona, the outermost layer of its atmosphere. It's a region that appears faint and ghostly in normal light, but through ultraviolet eyes, it becomes alive, shimmering, crackling, burning at 1,000,000 degrees Kelvin. Strangely, the corona is hotter than the layers beneath it, a fact that puzzled scientists for decades. How can the outermost region of the sun's atmosphere be hotter than its visible surface? The answer, we now know, lies in magnetic energy and plasma dynamics, invisible phenomena that only extreme wavelengths can expose. And here's something poetic during a total solar eclipse. For just a few moments, all of us can see this ghostly layer with our own eyes. When the moon blocks the photosphere, the corona becomes visible, a glowing crown dancing around the sun. It's a reminder that some of the most magnificent parts of nature are hidden in plain sight, waiting for the right conditions or the right lens to be revealed. Now, let's go deeper. Using even shorter wavelengths, around 30 nanometers, we begin to see regions in the corona where temperatures soar to 20 million Kelvin. These aren't just patches of heat. They're explosive events, solar flares, bursts of electromagnetic radiation that ripple through the solar system like shock waves from a star quake. These flares are the sun's most dramatic outbursts. They're caused by the sudden snapping and reconnection of magnetic field lines flinging charged particles into space at near relativistic speeds. One particularly active week in August 2022 saw dozens of these flares, some of them large enough to disrupt radio signals and satellites on Earth. But flares are just the beginning. The sun's outer layers host a range of strange, dangerous, and beautiful structures, each of them visible only through specialized wavelengths. It's as if the sun is veiled in mystery, and with each new band of light, we explore a new truth is revealed. What we see with our eyes is only the beginning. The real sun, the one teeming with storms and currents and violent beauty, is hidden behind the veil of visible light. To study it properly, we must become fluent in the full spectrum of light itself. The corona may look delicate and ghostly in images, but don't be fooled. It is a region of raw, unrelenting power. Using extreme ultraviolet light, we see it for what it truly is, a realm of magnetic chaos and searing plasma stretching millions of kilometers into space. Within this realm, two of the most impactful phenomena occur: solar flares and coronal holes, and both are responsible for sending shock waves across the entire solar system. Let's start with solar flares. They begin as tension in the sun's magnetic fields. Deep within the sun, currents of plasma churn and twist magnetic field lines until they become unstable. Suddenly, snap, like a tightly coiled rubber band releasing magnetic energy, explodes outward in the form of light X-rays and particles. These flares are so powerful they can reach Earth in just minutes and disrupt satellites' radio signals and power grids. Watching a solar flare erupt is like seeing a cosmic dragon breathe fire, hypnotic, dangerous, and magnificent. But the sun doesn't only explode outward. Sometimes it opens up, Coronal holes, which appear as dark patchy regions on ultraviolet images, are areas where the magnetic field lines don't loop back toward the surface, but instead stretch straight out into space. These are the leak points in the sun's magnetic envelope portals through which solar wind escapes. Solar wind is a stream of charged particles flowing out from the sun at hundreds of kilometers per second. When this wind reaches Earth, it collides with our planet's magnetic field, and that's when something magical happens. The energy from the sun interacts with atoms in our upper atmosphere, releasing beautiful dancing lights near the poles, the auroras. Greens, purples, reds, painting the night sky in swirling colors. It's one of the most visible ways we experience the sun's power on Earth. But this beauty comes with risk. During periods of high solar activity, like during the solar maximum of the sun's 11-year cycle, coronal holes become and more frequent. Solar winds intensify. Stronger winds mean more geomagnetic storms. And those storms can knock out communication satellites, cause GPS errors, and even overload power grids. Something that happened in Quebec in 1989, plunging millions into darkness in a matter of seconds. Yet these threats are also clues, signs of how interconnected we truly are with our star. With each coronal hole flare and burst of wind, the sun reminds us it is not a static light in the sky. It is alive, volatile, and in constant dialogue with the space around it, including Earth. And so we continue watching. Thanks to missions like the Solar Dynamics Observatory, we now have the ability to see these invisible storms unfold in real time. By studying the sun through ultraviolet and X-ray lenses, we gain more than just knowledge. We gain foresight, prediction, and protection. Because in space, the difference between knowing and not knowing can be the difference between light and darkness. Amid the chaos and searing heat of the sun's corona, something strange and almost graceful happens. Great arcs of plasma rise high above the surface, held aloft by magnetic forces that weave like invisible puppet strings. These structures, some small, others stretching over hundreds of thousands of kilometers, are known as solar prominences or filaments when viewed against the sun's face. They look like glowing ribbons suspended in midair, but they are anything but delicate. These prominences are composed of dense, cooler plasma held in place by magnetic loops extending outward from the photosphere. From Earth's perspective, they form loops so vast they could engulf entire planets. A single prominence might measure 10, 20s, even 50 times the diameter of Earth, yet appear tiny in solar images swallowed by the sheer scale of the star. And they move slowly at first, almost like they're floating, until they don't. In time-lapse footage, prominences can be seen twisting and writhing like serpents made of fire, coiling upward before collapsing, sometimes violently. This collapse isn't random. It's often caused by changes in the magnetic structure holding the plasma in place. When the magnetic loop destabilizes, just like with solar flares, the energy is released in an instant. But not all prominences explode into space. Some simply fall. This brings us to one of the most beautiful and surreal phenomena in the solar atmosphere: coronal rain. Imagine this charged plasma is ejected into the corona, lifted by a magnetic field. It cools rapidly, condensing like rain clouds do on Earth. And then, with nowhere else to go, it falls streaming down the magnetic field lines like glowing liquid fire. These shimmering showers are often invisible to the naked eye, but ultraviolet and extreme UV imaging allow us to witness them in stunning detail. They appear as golden tendrils or glowing droplets, some falling in smooth arcs, others splashing onto the surface like fire meeting fire, and they fall at incredible speeds. Coronal rain can descend at 100 kilometers per second, almost 300 times faster than sound returning to the surface with a force no storm on Earth could match. Each drop is millions of degrees in temperature. Beautiful, yes, but unimaginably hostile. This rain doesn't nourish crops or fill rivers. It's a recycling of energy and matter within the sun's upper layers, a glimpse into the intimate and violent conversation between heat magnetism and gravity. For centuries, people believed the heavens were serene, but the sun proves otherwise. Above its surface, plasma rises and falls, snaps and rains, dances, and explodes in a ballet so vast we can only observe in awe. And this is still just the atmosphere. The deeper we look, the more we realize the sun is not a glowing sphere. It is a storm suspended in space. And every prominence, every loop, every shower of fire is a piece of that living storm's expression. If solar flares are the sun's lightning, then coronal mass ejections, or CMEs, are its thunder. These are the most violent, far-reaching explosions. The sun can unleash immense bursts of plasma and magnetic field that blast off from the corona into space. Unlike flares, which are primarily bursts of electromagnetic radiation, CMEs involve the ejection of actual solar matter. Billions of tons of charged particles hurtling outward at over 1 million kilometers per hour. Just imagine a loop of plasma suspended above the sun's surface begins to bulge and twist. Slowly, over hours or even days, tension builds, magnetic lines stretch to the point of no return. Then suddenly, they snap. The result: a colossal detonation. In stunning time-lapse images, we can watch this moment unfold. What begins as a gentle arc transforms into a towering wall of fire, then explodes outward, sending a storm of ionized gas sweeping across the solar system. It's not just light that moves, it's matter with mass and force and momentum. And Earth isn't always out of the way. When a CME is aimed directly at our planet, it slams into Earth's magnetosphere with tremendous energy. Most of the time, our planet's magnetic field absorbs and redirects these particles harmlessly. But a strong enough CME, it can overwhelm our defenses. In 1859, during the Carrington event, a massive CME struck Earth and caused telegraph wires to spark and catch fire. Aurora Borealis was seen as far south as the Caribbean. And that was in an era with no satellites, no power grids, no modern electronics. If a similar event happened today, the consequences would be catastrophic. Satellites would be knocked out, GPS systems would fail, radio communications could go dark, entire electrical grids, including those that power cities, could be crippled. Some scientists estimate it could take months or years to fully recover from a CME of that magnitude in our modern world. But it's not just a threat. It's also a breathtaking spectacle. The CMEs we capture today, thanks to instruments like SDO, show swirling clouds of magnetized plasma expanding like smoke rings in space. They're beautiful, mesmerizing, almost poetic, if they weren't so dangerous. These events are most common during the solar maximum, the peak of the sun's 11-year activity cycle. During this time, sunspots increase magnetic activity surges, and both flares and CMEs become more frequent. Studying them helps us prepare. By tracking the sun's magnetic fields and predicting potential eruptions, space agencies around the world issue alerts for astronauts, pilots, satellite operators, and energy companies. Early warnings can mean the difference between safety and disaster. And that's the power of observation. Every time we look at the sun through a new wavelength, we don't just see more, we understand more. We anticipate, we adapt, we survive. Because even though the sun gives us life, it also tests our resilience. In the next section, we'll go deeper still into the transition region and chromosphere, where temperature spikes defy logic and plasma behaves in ways we're only just beginning to understand. Shall we continue? As we descend from the outer corona toward the sun's surface, we enter a narrow and perplexing zone, the transition region. This layer is thin, astonishingly thin, only about 100 kilometers thick, barely the length of a small city. And yet, in this short, vertical distance, the temperature skyrockets. At the top of the chromosphere, plasma might hover around 8,000 Kelvin. But just 100 kilometers higher, it explodes to over 500,000 Kelvin. That's an increase of more than 60 times in the space of a few breaths. It's one of the greatest temperature jumps found anywhere in the known universe, and for decades it baffled scientists. How can energy increase so dramatically in such a short distance, especially when moving away from the sun's core? The answer lies once again in magnetic fields, twisting, snapping, funneling energy upward, creating pockets of intense heat and pressure. To visualize this, NASA uses ultraviolet imaging at 160 nanometers a wavelength that reveals the swirling, pulsing nature of this zone. It's like watching boiling water. Only the bubbles are plasma jets erupting at speeds of hundreds of kilometers per second. Next comes the chromosphere, a turbulent semi-transparent layer approximately 1,700 kilometers thick. Just above the sun's visible surface, the photosphere. At first glance, the chromosphere seems calm, like a soft halo hugging the sun. But closer inspection reveals a landscape of chaotic movement. One of the most striking features here are the spicules, narrow jets of plasma that shoot upwards from the surface like fiery spears. They rise at incredible speeds, up to 100 kilometers per second, or about 282 times the speed of sound, and reach heights greater than Mount Everest. Imagine a vast field of fiery grass, each blade surging skyward, shimmering in and out of existence in just 5 to 10 minutes. That's the chromosphere. For years, scientists couldn't explain how these spicules form. The sun's strong magnetic field seemed to trap charged particles, making it impossible for them to escape with such force. But in 2017, a breakthrough came. A team of solar physicists introduced neutral particles into their model's particles. that have no electric charge and were previously thought to be irrelevant. Surprisingly, these neutral particles gave the magnetically charged plasma just enough buoyancy to break free, launching skyward in those magnificent spicules. It was a reminder that even in a realm ruled by heat and magnetism, the smallest forces can unlock the greatest motion. In a way, the chromosphere is like the skin of a star, thin, sensitive, reactive. It responds to changes from within and above. It connects the mysterious outer layers with the fiery core beneath. And while we're getting closer to the surface, the chromosphere still guards many secrets. It cannot be seen in visible light. But with the right tools, ultraviolet wavelengths, high-speed telescopes, and advanced modeling, we can now watch the sun's skin breathe. And what we see is breathtaking. Next, we finally arrive at what most people think of as the surface of the sun, the photosphere, a place that isn't solid but appears to be. A boundary that glows so intensely it defines our entire concept of daylight. Are you ready to meet the true face of the sun? When we look at the sun from Earth, what we're actually seeing is the photosphere, a glowing shell of light that defines the sun's shape, edge, and brightness. But here's the twist. The photosphere is not a surface at all. It may look solid, like a perfect golden disk in the sky. But in reality, the sun has no solid surface. The photosphere is a thin layer of plasma, roughly 400 kilometers thick, where light finally escapes after spending tens of thousands of years traveling outward from the core. It's the sun's final veil, the boundary between the star's deep interior and the vacuum of space. This is the light that gives us day. The photosphere burns at around 5 to 500 degrees Celsius or 5 to 800 Kelvin. Yet compared to the millions of degrees in the corona, it's relatively cool, which is why it shines in the visible spectrum that human eyes are tuned to. But look closer, and something strange appears. Scattered across the photosphere are dark blemishes, eerie, ominous patches that seem to mar the sun's golden glow. These are the sunspots, and they are far more than just surface imperfections. Sunspots are regions of intense magnetic activity. Here, the magnetic field is so strong, thousands of times stronger than Earth's, that it blocks heat from rising through convection. As a result, these areas cool down, slightly dropping to about 3,800 to 4,200 K, making them appear darker in contrast to the surrounding plasma. But make no mistake, they're still hotter than lava. Sunspots often appear in pairs or clusters connected by giant loops of magnetic field. These regions are not just passive features. They're often the birthplaces of solar flares and CMEs. When sunspots twist and shift, the magnetic field lines can suddenly snap, triggering explosions that send shock waves across space. Want proof? If you compare a visible light image of sunspots with an ultraviolet image taken at the same time, you'll often find solar flares erupting from the exact same locations. It's like watching pressure build under the crust of the Earth before a volcanic eruption. And then there's granulation, a stunning, almost artistic pattern that covers the entire photosphere. Under extreme magnification, the photosphere isn't smooth. Instead, it's composed of countless solar granules, boiling cells of plasma, each about 1,000 kilometers wide. constantly forming, dissolving, and reshaping. They resemble bubbling porridge or cracked lava. But these are actually the tops of convection currents rising from deep within the sun. In each granule, superheated plasma rises from the interior, glows brightly as it releases energy, then cools and sinks back down along the darker edges. These motions happen fast in each granule lives for only about 20 minutes, but the entire surface is constantly churning. The speed of these flows, over 7 kilometers per second, faster than a bullet, faster than sound. In fact, they generate sonic booms, sending shock waves that ripple across the sun's surface like tsunamis of heat and motion. So, that grainy texture you see in full disk images of the sun, that's not an imaging error. That's not static. It's motion, heat, and life recorded across millions of kilometers. From sunspots to granules, from convection currents to sonic tremors, the photosphere is the sun's loudest whisper, the glowing message it sends out to the universe. But here's the boundary. We've now reached the deepest part of the sun that light can escape from. Below this, everything becomes opaque. No telescope, no camera, no electromagnetic wave can peer deeper. Not yet. What lies beneath the photosphere, that's a story told not in light, but in theory, in vibration, and in math. And maybe one day, in new technology, still beyond our reach. But we're not done yet. In our final section, we'll look back at everything we've discovered. We'll explore why observing the sun in multiple wavelengths is crucial, not just for science, but for our survival. And we'll tell you how, for just a few precious minutes, you can see the sun's hidden layers with your own eyes. Shall we continue to the conclusion? So here we are standing at the end of light's journey. From the invisible storms of the corona to the rippling granules of the photosphere, we've peeled back the sun's outer layers with tools our ancestors could never have imagined. And what we've found isn't just knowledge. It's a new way of seeing. Every wavelength of light tells a different story. Ultraviolet reveals ghostly flares and magnetic loops. Extreme UV shows us violent storms and streaming solar wind. Infrared helps us trace heat. Visible light gives us the only face we thought we knew. And yet when combined, they paint a living portrait of a star in constant motion, breathing, twisting, erupting, and holding our lives in delicate balance. The sun isn't static, it's not simple, and it's certainly not silent. It roars through space with light and fire. Yet we never hear it, only see its echoes in auroras. Feel its warmth on our skin, and watch our skies light up when its storms reach us from across millions of kilometers. It reminds us of something deeply human, that what's most essential is often invisible. Without extreme UV light, we'd never see a coronal hole. Without radio telescopes, we wouldn't know when a flare is coming. Without mathematics, we'd never know how deep the energy flows inside. But there's one moment, a rare, fleeting moment, where you can witness something profound, not through a telescope, not on a screen, but with your own eyes. On April 8th, 2024, a total solar eclipse will sweep across parts of the Earth. For just a few minutes, the the moon will block the sun's blinding photosphere. And in that darkness, the corona will appear glowing tendrils of plasma reaching into the void visible without instruments. No filters, no satellites, just you and the sun's hidden face. It's an experience that leaves people speechless. Some cry, others cheer, but all are changed. Because for once, you're not just watching a star, you're meeting it. But to do so safely, you'll need eclipse glasses specially designed to block harmful rays while letting you admire one of nature's most powerful events. And thanks to Visi Solar, NASA-approved ISO-certified eclipse glasses are now available along with smartphone lenses to let you safely capture the memory forever. Don't miss this chance. The next total solar eclipse visible from the US won't happen again until 2044. And by then, who knows what else we'll have discovered about our star. So when that day comes, take a moment, step outside, look up, and remember that behind every beam of sunlight, there's a universe of energy, mystery, and movement waiting to be seen. Thank you for joining me on this journey through the sun. If you'd like to learn more, explore our other videos from Jupiter storms to black holes and beyond. A special thanks to our patrons and supporters. Until next time, stay curious, stay inspired, and keep looking up.